This is CS402 for Wednesday, July 23rd, 2014.
Kernel 3 is due in a little over a week. And again, if you have code from previous semester, don't copy from it. Best to get rid of it. Grading guideline is the only way to we will grade. And there are lots of tests in Kernel 3. So I'm hoping that by this time you should be working on the Hello program. Even if you got the Hello program to work, there's still a lot of stuff to do afterwards. There, many tests. There's something called mem tests that test the heck out of the virtual memory. So you should get enough to work to get Hello to basically running, and then start running these programs. As your kernel crashes, you start fixing those things that these tests is asking you to implement. All right. Okay, same thing as before, and I've been also adding stuff to the kernel fact. So please make sure you read it. There's a lot of useful hints that you can find in the kernel 3 fact. All right, so we are still in chapter 6. So I was going to remember that I mentioned that in the lecture slides. There are 7 things that we are planning to cover after chapter 7, right? So doing 1, 2, 3, 4, 5, 6, and 7. So today we're gonna finish chapter 6 and maybe cover a little bit of chapter 4, talking about devices. And then next week we're gonna cover the important topics of virtual machine and also scheduling. Okay, the last one, the shared library in chapter 3, we might not have enough time to cover that, but that's only like sort of a half an hour lecture. We might skip that in the end. So most likely the final exam will cover all the way to basically covering chapter 5, 6, and 7, and also with chapter 4 with devices and virtual machine. Anyways, when it's come closer to the final exam, I will post all the topics that I cover, and basically it's going to be everything after the midterm, all the way to the last lecture of next week. All right. Okay, so last time we were here talking about how to implement directories in the kernel, and we mentioned about this extensible hashing. So one way to improve the performance of directory lookup is to use a hash table, and turns out this particular approach, it was pretty smart that it used use indirection, so that when you rehash, you only write to small number of a disk block, on the disk, instead of if you use a generic hash table, every time when you rehash, you're going to end up doing a lot of disk writes. Okay, so this is a good way to go. Another approach to speed up directory lookup is to use B trees. So B trees is sort of the idea is similar to a binary tree, that you build a tree, except that every node is going to have tons and tons of child nodes. Okay, so B tree is a tree where the fan out, the number of children for a parent node is on the order of 50 or something like that. It's a very, very high fan out node, high fan out tree. So the idea over here is that when you construct a tree, the number of level is going to be really, really small. So when you need to look for something, you only have to read a very small number of nodes. Okay? So B tree over here it says, B tree usually is defined by the order of the B tree. The B tree of order M has a number of properties. So M is about the number of children a node can have. Okay? If B tree of order M, M could be like 5, right? So that means that every node has less than or equal to 5 children. Okay? And also every node has to have greater than or equal to M over 2 children. So if M is equal to 5, then M over 2 is 2.5, and the ceiling of 2.5 is equal to 3, then that means that this B tree, every node will have either 3, 4, or 5 children. Okay, so you cannot have less than, 3 children. If you have less than 3 children, then you have to do something to adjust the B tree. Okay, so the B tree has some sort of a balancing algorithm where if you have a node that has too few nodes, then there's going to be some balancing operation that needs to be done so that every node will satisfy this requirement. Okay, so this requirement can be validated at the root node and also the leaf node. The leaf node only has, basically no children. The root node can have actually less than that many children. Okay, and the reason for doing this is that this will guarantee that every node of size M is at least 50% full. Okay, so if you look at every one of these nodes, it can have up to M children, okay, but it has, have to have at least M over 2, children. That means that this node is at least 50% full. Okay, so this way we don't waste too much, disk space due to internal fragmentation. All right? Okay, what else, does the B tree have? Let me get rid of this thing here. Okay, the root has at least 2 children unless it's also a leaf. If the root is a leaf, then that means that you only have 1 node in your entire B tree, so that's a sort of a degenerate case. And then here's one funny thing about B tree is that all the leaf nodes appears at the same level and carry no keys. Okay, so when you draw the B tree, you only draw the internal nodes, you don't draw the leaf nodes, okay, because the leaf nodes are the ones that contain data. And all the leaf nodes, so in the end, if you have a lot of fan out over here, these are the leaf nodes. The leaf nodes are the ones that contain data, and everything in the middle, they all contain, only pointers. Okay, so therefore you can think about this B tree as a indexing structure, okay, that puts an index on the actual data. So at the bottom over here where you have the leaf node, this is the data, okay? Everything on top of it is an index structure, okay? And in computer science, when you said you have an index structure, that means that it's a data structure for you to help you to, to look things up efficiently. Okay, so this is just a data structure that helps you to speed things up. All right, and at the bottom is where you store the data. And for B tree, all the leaf nodes appear at the same level. Okay, so this is very, very different from binary tree, right? If you have a binary tree can look like this. Okay, where you have a leaf node at level 2, a leaf node at level 2, and a leaf node at level 1. But for B tree, this cannot happen. All the leaf nodes are all at the same level. Okay, so it's kind of a weird, tree. Okay, we're not really going to get in too much into it. If you take a database class, you will know all the gory detail of B tree. So we just sort of, give it an idea without getting too much into it. All right. Okay, the important thing about B tree is that every node in a B tree corresponds to a disk block. Okay, so this node is the size of a disk block, and that's pretty much how you determine what M has to be. Okay, so this node can have at most M children, so you use that to figure out how big of this block, and you can figure out exactly what M has to be. Okay, so every one of these nodes, they all fit in exactly one disk block, and similarly, these data blocks over here, the data nodes, they also fit exactly onto a disk block. All right, so this way, since the tree is going to be very, very short, if you need to get some data, you go to the root node, and you go to, one of the intermediate node, and then pretty soon you're going to get to the data. All right, so again, this is very similar. I guess the basic idea is similar to the hash table, is that you want to be able to get to the data in 1 or 2 disk reads. Okay, you don't want to have too many disk reads because that tends to slow down your file system. All right, every node in the B tree corresponds to this block, and then there's something called the B plus tree. As it turns out, there are, 20 variations of B tree. That's why you have to, take in the database class to look at all the different B trees. One of them is called a B plus tree, is that in addition to this particular data structure, at the bottom where you have all the data blocks, the data block actually has a pointer that points to the next data block. Okay, so this way, similar to a binary search tree, if you look at the index structure, then all the data are sorted, okay, when you try to visit the binary search tree. So in this case, the B tree also will be sorted, but if it's sorted, you can just walk down the leaf of the tree and you will retrieve all the nodes in your tree in a sorted order. Okay, so in that case, what is the order over here? Well, it's just a linear order over here where all the data will be sorted. Okay, so if you do something like this, then if I find the first node over here, in order for me to get the next larger node, I don't have to go up and down the B tree anymore. I can just do a linear search down at the bottom. Okay, so if you have links down at the bottom node, then this is called a B plus tree. All right. Okay, and also the internal node contains no data, just keys. So this is what I mentioned before. It's just an index structure, and the bottom has a pointer. There are lots of B-tree variation in various application area. We will just illustrate the basic idea with an example. Okay, the actual B plus tree algorithm is a lot more complicated than the one I'm going to show. Okay, and the one I'm going to show is sort of basically show you how a B tree becomes bigger. Okay, and also how a B tree becomes smaller. All right, there are other operations that can avoid a tree to grow. Okay, here's an example of a B plus tree. M is equal to 3, right? So 3 divided by 2 is equal to 1.5. The ceiling of 1.5 is equal to 2. So every node can have 2 or 3 children. Okay, they cannot have 1. When you have 1, you have to do something. Okay, so this particular tree, this guy has, 3 children, right? This guy has 3 children, and this guy has 2 children. Okay, and the way that it works is very similar to a binary search tree. When you try to look for something, you look at the keys in the internal node to decide whether you want to go left or right. Okay, but in this case, there are multiple keys in them, so you sort of have to look at, the string that you're looking for. Where is it? Okay, so here's an example. If you want to look for the string Lucy, right, you start from the top. Okay, and then there are 2 keys in the internal node over here. One is Ivan and one is Richard. So you say, well, is Lucy less than Ivan? The answer is no, right? L is after I, so Lucy is bigger than Ivan. Is Lucy, less than Richard? The answer is yes, so therefore you follow the middle pointer. Okay, very similar to binary tree, except have more pointers. You come to this node. Is Lucy bigger than Lisa? The answer is yes. Is Lucy less than Otto? The answer is yes. So therefore, you follow the middle pointer over here. And then you get to a leaf node. The leaf node is where you store all the data. Okay, in this case, the data that you have are Lisa, Matthew, and Nicole. Which means that the lookup of Lucy failed. Okay, so this is very similar to binary tree. If you want to insert something, what you need to do is that you need to look up the data first. If you can't find it, then you can insert it. If you can find it, then you already have the data there, so you can't insert the same data twice. All right, so in this case, we found that this is going to be the node we're going to insert Lucy. If we put Lucy in here, in this example, this node is going to be too full. Okay, and this node we actually only have 3 pieces of data over here. Then what can we do? Okay, so in a real B tree, what you need to do is that you need to look around that particular node to see if you can move some data from this node to the neighboring node. Therefore, you can create space in this node. So in this case, it is possible. You can see that if you go down to the bottom over here, and if you go in this direction, all the data entries over here are sorted. Okay, so therefore you can move the largest element to the right because the node to the right only has 2 things in them. So if you can move Nicole to the next one, then you have just created space for Lisa in this particular node. Okay, so in that case, what you end up doing is that you're going to end up with 2 disk writes. You're going to write to this node, and you're going to write to this node in order for you to insert, Lucy into the B tree. Okay. But in this case, again, we're not going to do that. We're going to try to create a new node, okay, so that you can see how B tree gets bigger. Okay, so since this node is full, the way that we can insert something new is to split up the node into 2 nodes. Okay, so we're going to create another node over here. Okay, and it's empty. And what we're going to do is that we're going to move some of the nodes from here to the other side. So what are we going to move? right? Since Lucy is over here, it's ranked second in this list, so we're going to keep the first one, the second one on the left, and the third one and the fourth to the right. Okay? What we're going to end up with is something like this, where Lucy and Lisa is going to end up over here, and then Matthew and Nicole is going to move over there. Okay? But I think I should go back to this picture. But if we add another node over here, that means that the parent node will have 4 children, and having 4 children is not allowed, so therefore the parent has to split. So this guy will split into 2, okay? Where the left side you will keep 2 children, and the right side you will keep 2 children. But the result of this is that this guy needs 4 pointers, and then this guy needs to split again. So the left side will keep 2 pointers, and the right side will keep 2 pointers. In this case, you will end up with a new node at the root. Okay, and this new root will have 2 nodes as children. Okay, so this illustrates that when B tree grows, it grows at the top. All right, so this is very different from binary tree. Right, binary tree, when you grow, you add stuff at the bottom. When B tree grow, you add a level on the top. All right, and this is how you can have the property that all the leaf nodes are always at the same level. Right, if you think about it, right, if you have a tree where all the leaf nodes are all at the same level, how can you ever grow? Okay, I mean, the only place to grow is at the top, right? All right, anyways, so this is an example where it shows that after you insert Lucy, you're going to get 1 more level. Okay, let's continue. All right, over here, sort of mentioned that another option is to, rotate Nicole to the right. So therefore, in this example, you don't really have to grow that tree to 1 more level. There are other options. If you want to delete something, right, if we start from over here, you delete Otto. Okay, we do the same thing. We do a lookup first. We go to the root. Okay, and Otto is greater than Matthew. We go to the right. Otto is less than Richard. We go to the left. And over here, Otto is less than or equal to Otto. Oh, sorry. If it's less than Otto, Otto is not less than Otto, so it doesn't go there. Okay, Otto is greater than or equal to Otto, so you go to the right, and you find Otto right here. And this is the entry you have to delete. Okay, when you delete this particular node, end up with too few data items. So therefore, you have to, move Paula either to one of the neighboring nodes. Okay, so in this case, Paula will be moved into this particular node. But when you do that, that means that this node becomes empty. When it becomes empty, this link is gone. Then this node only has 1 child. Okay, having 1 child is not allowed. Okay, so therefore, you have to merge that with the neighboring node again. In this case, this guy has 1 child and this guy has 3 child. You can merge them together so that into 1 node that has 3 child. But then the parent node only left with only 1 child, so you have to merge the parent node with its neighbor. So now you're going to end up with a new node with 3 children, and then the root is gone. All right, so similarly, when B tree shrink, it shrink at the top. All right, and again, all the leaf nodes are always at the same level. All right, so this, this example sort of demonstrate, how this actually works. Okay, and again, we're really at a very high level. This doesn't really, the operation that I show is really not any real B tree. Okay. All right. Okay, so the bottom line for B tree is that you want to minimize the number of disk reads, and every node over here corresponding to 1 disk block. Okay, so the read and write operation is minimized. Oh, and also the other thing that I forgot to mention is that as you deleting stuff and merge the node, you got to update the keys over here. Okay, so when I try to merge these 2 things together, okay, I also need to remember that I need to update the keys in the internal node. Those things also correspond to writes to disk. Okay, so in the worst case, the number of disk nodes that you have to update is going to be on the order of log, log n, and n is the total number of nodes, right? But the base over here is not base 2, it's base m, right? Because m is the number of children that you have. Okay, so hopefully this is going to be a small number even in the worst case. All right, again, much, much better than linear, right? Okay, so that's all I want to mention about B tree, okay? Again, database class has all the details. There's one more little thing about, this is falls under the heading of namespace management. If you want to have a file system that's very, very large, it spans multiple disks, what do you do, right? So for example, over here you have one file system, and then over here you have another file system, and these two file systems might be different file system, right? This might be ext3, and this might be, FAT32 or something like that. 32, not 33. So what you can do is that you can have one file system appear at the bottom of another file system. Okay, I think I mentioned something before that there was a project at CMU called the Andrew file system, and that file system, the idea here is that put all the file system in the world under one big tree. Okay, so therefore you're going to have file system appearing at the node of of another file system. Okay, so there are different ways to manage these namespace. On Unix, the way it's done is called file system mounting. Okay, so if we go back to this picture, you mount this entire file system onto one of the directory node over here. This guy has to be a directory node. Okay, so you can put the root node over here as if it appears right here. Okay, so how can you do something like that? I mean, if I am traversing, the file system, right? Think about your VFS, project. If you try to do some kind of a lookup, when I go to this particular node, I'm going to do an inode lookup. Okay, and currently, right now, you go down. I guess in VFS, you have the RAM file system. So you go to the RAM file system and continue to look up in the actual file system. Right. So over here, we're going to do the same thing. We're doing looking up in one file system. As you go to one of these nodes that have a file system mounted on it, then basically you're going to use polymorphism to have you to switch to looking data up in another file system. Okay, so using polymorphism, this actually can be done, quite easily. Okay, so that's how Linux and Unix do it. Windows, they don't really have something like that. Well, in the good old Windows, they have drive letters, A, B, C, D, and stuff like that. I guess with Windows NT, they can start to have file system mounting. All right, so in Unix, the command that I guess over here, here's an example how to mount one file system onto another. If you have a device called disk2 and you want to mount disk2 into onto the directory node /user, then the command that you can use is using the mount command, mount /dev/disk2 onto /user. Okay, so the idea over here is that you want to mount this entire file system, which is denoted over here, on a separate disk. Okay, it could be a sort of a different file system, FAT32 or something like that. You want to mount it onto this particular node. Okay, so this picture sort of shows you that you can use some sort of a polymorphism to have this entire file system appear inside the inode of the original file system. Okay. When you do that, right, if you say mount /dev/disk2/user, then what happens is that when you try to access a file, say /user bin/bash, so again, think about your VFS, VFS code, right? When you do a lookup, you're going to look up this guy, in the root system as before. You're going to find the user entry, and now user entry, that particular inode is going to describe that, oh, this is a file system mount point, and you have to switch to a different file system. Okay, so therefore from this point on, you're going to switch to a different file system because /user is the same thing as /dev/disk2. Okay, from that point on, the bin and the bash, they will be looked up in another file system. All right, so you can just pass that information to the other file system and to continue to look up over there. On Mac OS X, I guess instead of having so over here, the devices usually what they do in modern Unix is that they will create these directories on the fly as you plug in USB devices. Okay, so the USB devices sometimes they appear under the /mount directory. On Mac OS X, they just use a different name, but similar kind of mechanism, right? They use something called /volumes. That's where all the mounted file system goes in there. Okay, and the Mac, I guess they, every time when you download something, it's downloaded as if it's sitting on a separate disk, and it gets mounted into /volumes, and you can access it that way. For Unix, mounting by default is 0 in config.mk, so you can play around with it. Of course, after the semester is over, if you have, want to see how it's done, then you can play with this, right? Again, it's using polymorphism. All right, so there is one more thing left in chapter 6. And again, that's talking about, file system crashes. The file system crash that we talked about before was assuming that, you only have one disk and you try to worry about, that disk when it crashes, you want the data to be consistent. Okay? Now we're going to look at a case where what if the disk died? Okay, if a disk died, then all the data on the disk is completely gone, right? So it doesn't really matter if you use shadow pages or if you use journaling file system, then all the data there are gone. Okay, so what do you do? And also, modern disks, they die. They are not that reliable. I mean, they're reasonably reliable. When was the last time your hard drive died? When you buy a new machine, you expect, that machine to last, the hard drive to last for, at least 5 years. And by that time, you're going to get a new machine. So, you rarely see hard drive dies. Okay? But drive do die once in a while, and it's a horrible thing if you, lose all the data on that drive. All right, so we're going to see, how does the operating system cope with the fact that, the disk also, will be completely becoming inaccessible. So the basic solution is to look at, multiple disks. Okay, you're going to use more than one disk, and then one of the important technology that was developed, I guess, in the the 80s and 90s is called RAID. And these days you can go to Amazon, you can buy a RAID disk, and those disks are a lot more reliable than a single disk. All right, so when you put multiple disks and you group them together into one disk system, okay, there are some benefits, right? Clearly, you can hold more data. Okay, and also you can store data in a redundant fashion, right? So you have 4 disks over here. Okay, normally if you want to write one piece of data onto the disk, well, write another copy over here. So in this case, this disk died. You can just pick up the data right there. Okay, so therefore that gives you an opportunity to store data redundantly. This will increase reliability. Okay, because your system will not go down if this disk goes down, because all the data are back up in another disk drive. Okay, this also makes your system more available. Okay, it is possible that when this disk goes down, you don't even have to reboot your system. Your operating system can realize that, hey, the disk went down. It will just switch, to using the other disk. Okay, because normally we'll have access to all these disks. So the system doesn't even have to go through a reboot. Your system can continue to be available to the rest of the world. Okay. The other advantage, so once you have multiple disks, the other way is that the data can be spread across multiple devices, allowing parallel access. Okay, so what happens is that when you store one piece of data over here, and you get a copy right here, okay, now when the user tries to request this piece of data, well, you have a choice. You can either tell the file system to retrieve that piece of data from this disk or from that disk. Okay, so before, if you only have one single disk, then all the requests will come to this disk. So the load on that disk is going to be very, very high. The disk is going to be busy all the time. Okay, but when you have 4 disks, basically you can spread the load among these two systems. So if you have an entire copy of this disk over here, an entire copy of this over here, then in this case, you will split the load into 50% of the traffic will go to this disk. Well, 50% of the traffic that's supposed to go to this disk will go to either this one or this one. Okay, so therefore you cut down the traffic on the disk by 50%. And if you're going to hit this disk, now you can split it between these two disks. Again, cut down the traffic by 50%. Okay, so therefore things can be accessed in parallel. So therefore there's higher parallelism, and then the overall performance of the disk system, is going to be much better. Okay, so not only when you can improve reliability, you can also improve performance on your disk system. Okay, so that's why this is sort of a desirable thing to have. So in order for you to support multiple disks, and you don't really want to change the interface to your operating system, so the idea over here is to add additional layer inside your operating system to manage this disk. Okay, so the general name for this particular layer is called the Logical Volume Manager, or LVM. Right? The idea over here is that you have a file system that used to think that it's talking to the hard drive, okay, but now you put in this layer in between that's going to make all the disks collectively look like a big disk to the higher layer. Okay, so FFS over here, thinking that it's talking to one giant disk, the Logical Volume Manager knows that there are actually multiple disks. Okay, so therefore the volume manager, its responsibility is to actually hide all the details away from the file system, so that if you are using multiple disks for parallelism, it will do this seamlessly, across the file system. All right? And also, when the disk failed, the logical volume manager, will be acting as if the disk hasn't failed. It will pick up the data from the backup disk without the fast file system even know that this is happening. All right, so that's sort of the big trick down at the volume, at the bottom. The logical volume manager has choices of doing different things, and all these things are hidden away from the file system. For example, like I said, right, you can span, you can store data on both disks. So now you just have it look like as if you have a bigger disk. Okay, so that's a simple thing to do. If you want to provide reliability, you can do mirroring. That will add reliability to your system. Everything that's over here has a copy right there. But then you have to sort of worry about whether the disks are exactly the same disk or not. It has to have the same number of sector. Otherwise, it's going to be sort of difficult to have an exact mirror. Right? Okay? So it has to do all the copying and also doing load balancing by splitting the load among these two systems, two disks. Other things that the logical volume manager can do, if you have more than two disks, there are even more options. So one thing that you can do, you can stripe your data across the disk. Okay, this example over here, I have 5 disks. Okay, when I try to put data on disk, I don't have to put the data on all 5 disks. I can actually stripe it across several disks. Okay, so for example, I can divide my file into multiple units. This example, I divide my file into 20 units. I'm going to put the first unit on this one, the second unit on this two, the third on the third disk, and the fourth on the fourth disk, and the 5th unit, I'm going to put it back on the first disk. 5, 6, 7, 8, 9, 10, 11, so this file only goes on the first 4 disks. Okay, it doesn't, maybe there are more disks, there are 6, 7, 8, 9, there are lots of disks. It's like a disk farm, has tons of, disks out there. This file only goes on to the first 4 disks. Okay, I'm going to stripe it across because the way the disk block is going to be organized is I'm going to go through this disk in sequence. When I reach the last one in the group, I'm going to go to the next one, etc. Okay, so when I do this, then when I try to retrieve files, retrieve data, okay, if I need the first 4 disk block, instead of doing 4 reads on the same disk, I will do 1 read on 4 disks. Okay, so therefore, when I retrieve unit 1, 2, 3, 4, they will come back much, much faster. Okay, and the reason they're coming back much faster is because I only have to do 1 seek on each disk, and they are done in parallel. So therefore, the response time in terms of seek is going to be the worst response time out of the 4. Okay, if you only have 1 disk, then you're going to end up with 4 disk seek, in that system, and then you sort of have to worry about how you lay out these blocks, so they have to be right next to each other, so that when you retrieve all 4 of them, it's going to be fast enough. Okay, this way, if you put it on 4 different disks, then, in a way, it doesn't really matter where they are. Okay, so it will actually make the system maybe a little easier to design. All right, so what is the unit size? Okay, when I said divide the file into 20 units, theoretically, a unit can be a bit, right? So I'm going to put the first bit over here, the second bit over here, third, fourth, etc. Okay, and then, for this file, everything that go onto the first disk, I will pack them into a sector before I write it into that particular disk. Okay, so this is called bit interleaving, right? After you put 1 bit on 1 device, you put the next bit on the next device and the next bit on the next device. Okay, so that, I mean, in a way, it's kind of silly. Why put a bit on the disk? You can actually put blocks on the disk because that's how this works, right? All right, so by the way, the number of disks that a file goes across, this is called, when you perform striping, this is called the stripe width. Okay, the stripe width is the number of disks that you stripe across for this particular file. This example, stripe width equal to 4, even though you might have many, much more than 4 disks. All right, so the parallel disk, right, the advantage is that you can reduce access time because you can do things in parallel, and increase parallelism. Disadvantage, so when you have 4 disks, and then you try to access these 4 disks, then sort of the response time is going to be the worst case of the 4. Okay, these 4, right? 1, 2, 3, 4. Maybe it has just so happened that A, B, C, those disks are, not very busy, and the 4th disk is very, very busy. If you put all your data on disk A, and if you just hit this A, and then you put the block right next to each other, then you're going to have you're going to have one seek time followed by all these incremental seek time, which are very, very small. Right? So you can end up performing really well, but when you put it on 4 different disks, this guy just happened to have a lot of load hitting this particular disk, then the last guy is going to be the slowest one, and then the response time is going to be the response time of the slowest disk. Okay? So therefore, the access time to the disk, if you look at all 4 different disks, then there's going to be a high variation. Okay? So the variance is high, right? Average might be, normal across all the disks, but in the end, the variance is what's going to kill the performance. Okay? Because you always look at the worst case, performance. So multiple disks end up with higher variance. Another funny problem is that you're going to have worse reliability. Okay, if you only have a single disk, that disk is going to fail whenever it's going to fail, right? If you have 4 disks, then your system is going to fail when the first disk fails. All right, so again, there's going to be variation in all the 4 disks. Some disks are going to die earlier, and some disks are going to die later, but your system is going to fail when the first disk died. Okay, so therefore, you're going to end up with, in general, worse reliability. Okay, if you have a disk farm that has 1,000 disks, okay, think about, one of the cloud company have tons of, disk and a machine, sitting in a machine room somewhere. If you walk into that room and you say, are all the disks working? Okay, the answer most likely is going to be no. Some of the disks will be dead. All right, so if you have a system with a lot of disks, chances are when you walk into the room, there's going to be some dead disk. Okay, so therefore, even though there are these advantages to parallel disk, you have to deal with the reliability problem because there's always going to be some disk that's dead. All right? I mean, you can actually use some equation to figure that out. Also, the disks are not all the same, right? When you have a disk go bad, you replace it with another disk. What if that model is not there? The manufacturer doesn't manufacture that anymore. You have to get a bigger disk, and every disk has different performance characteristic, right? So the idea in the beginning, when you have 4 identical disks, is that sort of the behavior of the system is more uniform and more predictable. And now you have disks that goes at different speed and different size. Then management is going to be a little more complicated. Okay, so your logical volume manager now have to worry about, oh, this disk is not the same size as that disk. How do you perform mirroring, on these disks? So it's going to introduce complexity in your software. All right, so I guess the textbook mentioned this term, concurrency factor. So it basically tells you, how much concurrency you can have. If you have 4 disks in parallel, you can have a concurrency factor of 2. Okay, and then sort of make the comment that the larger the concurrency factor, the less important striping is. Okay, so therefore, in general, performance is better with larger striping unit. All right, so I'm using this picture to sort of explain the last point. When you have 4 different files and you try to stripe it across 4 disks, okay, you have a choice of how you want to stripe this. Okay, so you can try to figure out what is the unit, what is the stripe unit size, right? I mentioned that stripe unit can be to 1 bit, okay, and it can be 1 block. Well, what about multiple blocks? Okay, so this comment over here is saying that when you have things that you can access in parallel, the more things you can access in parallel, the higher the concurrency factor is. Then what you want to do is that you want to do less striping. Okay, so in that case, if I have file 1, 2, and 3, and 4, okay, instead of striping every file among 4 disks to look like this, maybe it's more beneficial to have a larger striping unit to stripe the, to keep 1 file on disk 1 and 1 file on disk 2, 3, and 4, and make sure that when they go onto the disk, they are in consecutive sectors. Okay, so you can see that in this sort of contrived example, if you want to read all 4 files, okay, what's going to happen is that if you go with the first approach, you're going to have 1 disk seek over here, and 1 seek over here, 1 seek over here, 1 seek over here. All these 4 seeks can be done in parallel, so you're going to end up with, sort of the worst case seek time of 1 disk. Okay, if you actually stripe these files across 4 different disks, and when you try to retrieve all these files, then on this disk, you're going to end up with 4 seeks. and 4 seeks, and 4 seeks, and 4 seeks. Okay, the data transfer time, so remember, right, the access time of the disk has 3 parts. There is, seek time, rotational latency, and then transfer time. Okay, the data transfer time, that's just the maximum speed of your disk, and they are the same in either cases. So the only thing that really matters is the seek time. Okay, so looking at this picture, this one actually has a much better seek time than the other one. Okay, so in general, if you have a lot of concurrency, you try to stripe as wide, the stripe unit you try to use as big as possible. All right? Okay, and this slide over here basically tells you, when you have, too many disks, why does the reliability of the entire system go down? And actually it goes down to very, very, the reliability actually, goes really bad really fast. Okay? Over here, this says that if you assume that all the disks fail independently, that means that if you have 1,000 disks, okay, all the disks, the failures are not related to each other, they're totally independent, and they'll all have the same distribution, the failure characteristic. All right, so over here it says that we're going to assume that the failures are IID, which means that they're independent and identically distributed. Okay, every disk has some kind of a failure probability as time goes by, and then it's going to look like this. This is time, okay, and this is the probability of failure. What happens is that in the beginning, well, it depends on what kind of disk you have. Some of the disks are like this. They can fail at any time. Doesn't really matter how long you've been using it. Okay, and then there's some of the disks look like this. The older this is, the higher the failure rate. Okay, over here we're going to say that, well, all the disks has exactly the same picture. All right, so if that's the case, we can actually do some simple analysis to ask, if you have an n-disk system, what is the probability that all the disks are alive? Okay, so the probability a disk fail is going to be this F right here. Okay, so a single disk fail, the probability is F. So the probability that you have n disk and none of them are failed is the probability that all of them are working, which means that all of them are not failed. And the probability of any disk that's not failed is 1 minus F. If all of them are working, then the probability of that is 1 minus F to the nth power. Okay, so this function is an exponential function. Okay, so that actually it goes, it blows up really, really fast. Okay, so this is the probability that that none of this failed, and if you want to see that the probability of the system failed is 1 minus that probability. Okay, so this one you can actually plot it, using MATLAB or something like that, and you can see that as n starting to get large, no matter how reliable the disk is, okay, the probability of this failure might be, 10 to the minus 6. Okay, that's a very, very small probability that you have a disk fail. But when you have 1,000 of these disks sitting in a room, then all of a sudden the system failure rate becomes very large. All right, so you have a system of a lot of disks. At any time there's going to be some failed disk, and then you're going to end up with system rebooting all the time. Then that's really not a very good system to have. So the solution to this problem is called RAID. Okay, and RAID stands for redundant array of inexpensive disks. Okay, so this technology was invented by IBM because IBM was well known for making the opposite, making the large expensive disks. Okay, IBM actually has a sort of a disk business that all they made are disks, and they made a lot of money in the good old days. Okay, and then they're starting to realize the benefits of having redundancies, and then they discover that there's this problem with reliability, and then they start trying to solve this problem. Okay, so this is the solution they come with, a redundant array of inexpensive disk. They combine striping and mirroring, okay, and the basic idea is that when you have disk that goes out, you don't want the system to fail. Okay, so clearly if you have mirroring, well, that's one simple way for the system not to go down. Okay. But what are the other options? Okay, so there were 5 different variations that were originally defined when RAID is starting to become popular. Level 1, so these are called RAID levels. RAID level 1 through 4 were developed by IBM, and then RAID level 5 was developed by UC Berkeley, and RAID level 5 was the one that made the RAID system very, very famous because it's really, really nice design, and it has, it sort of solves some of the problem that the IBM system had. Okay, so these days, a lot of people will say, oh, RAID was invented by Berkeley, but turns out that's not the complete story. All right, I guess they, in the beginning they called RAID level 0 to be, well, they renumbered the system, since the early days. Okay, so we're going to sort of briefly go over what these RAID levels are, and every level is a little more, sophisticated and also better than the previous level. Okay, level 1 is just mirroring. If you have 2 disks, then every time when you try to write to a disk, right, if this is the write operation, okay, you try to write to this disk, what the logical volume manager is to make sure you write to the same place on the other disk. Okay, when you perform a read operation, okay, the logical volume manager is gonna toss a coin, or I guess it doesn't really toss a coin. They look at the queue on both disks, pick the one that's smaller, and then schedule the read onto that disk so that it can have a faster response time. All right, so and in this case, when the disk goes out. Okay, when the disk goes out, then you don't really have any choice. You only go to one disk for both read and write. Okay, and also what you need to worry about is that when the disk goes out, what you need to do is that you need to repair the disk, right? Because you want to bring the system back to operational by plugging in some sort of a spare, okay, and then copy everything from here over here, and then continue your operation. Okay, so part of the system design is that even when a disk fails, when you bring a spare, when you spin up a spare to try to replace the dead disk, you also got to worry about, when you implement your logical volume manager, is how to repair this disk so that this disk looks exactly like this disk, and you can go back to the previous configuration. All right, so that can also get complicated. RAID level 2 is basically using, error correcting code. Right, error correcting code is something that we use on memory. Okay, when you buy a piece of memory these days, right, you can buy, sort of a simple memory. And also you can buy memory with I guess the simple memory comes with a parity chip, right? So you're going to end up with a memory card where, over here there might be 8 of this thing, okay? And then there's an extra chip for parity. All right, so so this is memory. So what happens is that when you write to a particular memory location, you will write the parity so that if you add up all the bits, you're going to get an odd number. Okay, so this way, when you read the data back, okay, you can check the parity by adding up all the bits to make sure that they're equal to the parity. Okay, if they are not equal to the parity, that means that one of the memory chip is dead. Okay, and again, that's sort of the problem with memory that I mentioned before, that there's really no way for you to know whether you have memory or not. Okay, the only thing that you can do is you can write something to it and read it back to see if it's what you read back is what you wrote. Okay, so over here, we can use this particular scheme to determine whether a memory chip is dead or not. Okay, this particular scheme using a single parity will tell you that, so if the parity doesn't add up, then one of the memory chip is dead, but you don't know which one. Okay, it could even be the parity chip that's dead. Okay, so using coding theory, right, you can do error correction code. So in that case, you can also buy memory boards with error correcting code. In that case, for a memory chip out here, you're going to end up with additional parity chips. I guess for A, you might probably need 4. So clearly, this is a lot expensive, right? So this has increased the overhead in terms of the memory chip you have to have by 50%. Okay, so you can use this code so that when one of the chip dies, okay, so you got to figure out when you write a pattern into memory what to write in these parity chips, so that when you read them back, you can actually figure out which chip is dead. Okay, so usually you have you have error correcting code in memory for these kind of system. When one of the memory chip is dead, you can actually continue to function because you can figure out what kind of data was actually stored in that particular chip. Okay, so even though that chip is bad, you can reconstruct what's in that chip. Okay, so you can do single bit error correction, but you can do multiple bit error detection. If 2 chips are dead, then this board will say I'm dead. Okay, but if only 1 chip is dead, it will continue to function. Okay, so in RAID level 2, basically they just use exactly the idea from memory error correction and do exactly the same thing. You put the data bits on these disks, and then you put these check bits, the parity bits, on the other disk. Okay, so this way, if a disk goes dead, you can actually figure out everything on that disk by reading all the parity bits. Okay. But as it turns out, this was really silly because the disk is nothing like memory. Okay, memory, you don't know if it's dead or not, but the disk, you actually know it's dead or not. The disk, when it dies, it's going to raise its hand and says, I'm a dead disk. Okay, so therefore, it's kind of silly to have all these check bits. Okay, so that brings us to level 3, that you only need one parity bit. Okay, so what happens is that if I'm using, odd parity, okay, what I would need to make sure is that when I perform a write across all these disks, when I add up all the bits over there, I'm going to get an odd number, right? The least significant bit is going to be equal to 1. Okay, so in this case, if this disk goes dead, I would know that that disk is dead. In order for me to figure out what's on this disk, basically I just read the parity disk, add up all the bits, and if it's equal to 0, then I know that this bit has to be 1 on that disk. If it's equal to 1, then I know that this bit has to be 0 on that particular disk. Okay, so all we need is that we need one extra disk to store the parity. Okay, so this is RAID level 3. But again, this is using bits, and if you deal with bits, you have to pack bits into blocks, and that's too much extra work. So therefore, the RAID level 4 is basically saying, well, instead of using parity bits, I'm using parity blocks. Okay, so when I write a page at a time, right? When I write a page onto these disks, I'm going to compute. Let's say if I'm using odd parity, I'm going to add all these pages together, look at all the significant bits of every byte, and then figure out what block to write on the parity disk. Okay, this way, when one of the disks dies, and again, I read all the disk, all the disks, including parity disk, and then I can compute exactly what's on this disk, and so the system continues to operate. All right, so this is RAID level 4, right? It works pretty well. Right? When you have a disk die, then it can continue to operate. Okay, so clearly if you have 1,000 disks or even more than that, then the chances of 2 disks dying is going to become pretty big. Then this particular scheme is not going to work. Okay, and also when you have that many disks, then what happens is that you can actually divide the disk into different groups. So you have 500 disks over here, 500 disks over here, 500 disks over there. Then the chances of having 2 disks dying in 500 disks is a little less than 2 disks dying in 1,500 disks. Okay, so you sort of spread out your risk among these disk systems. All right, so in this case, what happens is that when you perform a write operation, what needs to be done? Okay, if I want to write only one disk block, right, because this file, I'm going to stripe it across all these disks. Okay, so if I only modifying the 3rd block, I'm going to write to this particular disk. Okay, so in that case, I also have to modify the parity disk. Okay, because the parity always have to add up. So every write now turns into 2 writes. Okay, and in order for me to compute the parity right here, I need all the data from all the other disks. Okay, so again, my buffer cache needs to work pretty well because all the other disk block has to be there. Otherwise, I have to go read it and then write it out, and that becomes really, really slow. Okay, so this scheme only works if the buffer cache works pretty well. All right. So what happens is that you're gonna end up with a system. So let's say that one of the disks is dead. Okay. So now, whenever you try to write to this disk, okay, you also have to write to even under normal operation. Let's put it this way: normal operation, when you write to this disk, you have to write to this disk. Okay. Another process is user process modifying data on this disk. Okay, what it ends up is that they also have to write to this parity disk. Okay, so if you have, in this example, 2, 4, 6, 8, 10, you have 10 disks over here and 1 disk over there. Okay, if you have 10 parallel writes to all these disks, you end up with 10 times the load going into your the parity disk. Okay, so again, you're going to end up with a sort of a variation. And you're really not finished writing until you write both finishing writing to the data block and also the parity block. Okay, so therefore, the write performance actually suffer with RAID 4 because, the parity disk is going to get too high of a load. Okay, so this, the solution for this comes in RAID level 5, which was developed at Berkeley. All right, so RAID level 5, get rid of the parity disk. Okay, so the idea over here is that whenever you try to write to a particular file, you're going to stripe it across the disk, but, what you do is that, let's look at an example. If you have a stripe width of 4, I'm going to write block 1 here, block 2 here, block 3 here, block 4 here, okay? And I'm going to write the parity of 1, 2, 3, 4 on the next disk. Okay, so this is going to be 1, exclusive OR with 2, exclusive OR with 3, exclusive OR with 4. I'm going to write the parity right here. Okay, and then I'm going to write the 5th block over here, 6, 7, 8. Okay, and then 5, exclusive OR, exclusive OR 8, the parity over here. And then 9, write it right here, 10, 11, 12. Okay, and write the parity right here. 13, 14, 15, 16, write a parity over here. 17, 18, 19, 20, I write the parity right here. Okay, so now you can see that the parity blocks are spread evenly among all the disks. Okay, so therefore the performance problem in RAID 4 is being solved by, using, by spreading the parity blocks all over the disk system. Okay? So you got to make sure the stripe width is going to be less than the number of disks. Okay, so therefore when you stripe across all these disks, you're going to end up have even loads in all the systems. Okay, also in this case, if a disk is dead, you need to sort of figure out where the parity block is. So basically, all you have to do is do a little bit of math, and you can figure out that if you want, block number 20. Okay, and this is dead, then you need to read, this number 10, number 11, and number 1, and number 3 in order to figure out what data is actually over here. Okay, so the complexity is increased a little bit, but the overall performance of your disk system is a lot better. All right? Okay, so that's all I want to say about, RAID 5. So there's actually one downside of RAID 5 is that if you try to add another disk into the system, okay, so what happens when you try to add another disk? You basically have to restripe everything. Okay, so it's kind of expensive to add an additional disk. Okay, otherwise RAID 5 sort of wins over RAID 4 in every comparison. So as it turns out that this storage system, I guess ever since people started to do RAID, this thing even become a separate field in computer science. Okay, so computer science, you can actually have people specialize in operating system, there are people specialize in just the file system, and now there are people actually specialize in the storage system. They have their own conferences, their own researches. The RAID become also crazy. After RAID 5, there's RAID 6, RAID 7, there was RAID 8. There's tons of RAID, that was invented after that. Okay, so anyways, if you can actually take I guess once in a while the CS department will actually offer a 599 class in storage systems. So if you're interested in storage system, there are plenty of things to learn there. All right, so that's all I want to say about RAID. The next thing is mention a little bit about what's these days we have flash drives. So flash is a little different. It's kind of different technology compared to disk, right? The disk we always draw like this. Okay. And the important thing about this picture is that it's circular, right? Because it's mechanical and it spins like this. Okay, so therefore, whenever you try to retrieve data, you got to worry about seek time. You worry about rotational latency. All that thing adds to the response time of the disk. Okay, the flash memory, right? It's a USB, disk. USB disk is based on flash, and if you have SSD hard drive, they are, they're based on the same technology. So in these cases, these devices, you can treat them as memory. Okay, so they are, you draw them like a, rectangle. So they are like memory in the sense that no matter which location that you access, it's the same latency. Okay, so the access time doesn't have all these other mechanical components. All it has is the data transfer time. All right, even though writing might be a little different. So this device is a little different from regular memory. Regular memory is very high speed. This one is, sort of slower, 1,000 times slower than, real memory. Okay, but it's, it has very good performance. All right, so for these flash memory, the advantage of these devices is that they pretty much look like the disk without the downside of disk. Okay, you can read these devices one block at a time. So therefore, we can reuse all the file system code because the file system code is dealing with blocks. So they basically, if you instead of having disk, you have flash memory. Well, the code pretty much work as is. Okay, so therefore that's a major advantage, right? The system, you like to use that. There's no seek, no rotational latency. That means that access one location is going to cost you exactly the same as accessing another location. So therefore, when you try to put data on the flash, flash devices, you don't have to think about where do you want to put it. Okay, like the disk, you have to say, oh, I have to create cylinder groups so that these things, go together. Well, you don't have all that complexity when you deal with flash devices. Their power, they're low power, they're vibration resistant, right? That's what we carry in our pocket. We don't have any problem with that. There's one downside with flash memory. Okay, so this is kind of counterintuitive. The flash memory actually has limited lifetime. Okay, so if you have a choice to store data on a hard drive, which is the mechanical device, and a flash, basically it's a solid state device, okay, where would you prefer to store that data? Okay, if you store it on the disk, chances are the disk is not going to die. If you store it on the flash drive is actually going to die before the hard drive. Okay, so the flash is really not a good place for long-term storage. Okay, and we're going to sort of briefly explain why that's the case. The other one is that flash, to write to the flash, it's asymmetric. Okay, not like memory. Memory read and write is about the same speed. The disk read and write is about the same speed. For flash, when you try to read from it, it's actually much faster than writing to it. Okay, because writing to it needs to go through some operation. So in that sense, if you think about you having a buffer cache, then the read and write, in a way, it's kind of similar to this system, right? The read characteristic and the write characteristic, they are asymmetric, right? When you write to the buffer cache, and later on, the data get written to disk. When you read, the data sort of basically comes in pretty fast, and they're already in memory. Okay, so the read and write are asymmetric. It costs a little more than disk, right? So I guess these numbers are 2000, last year's numbers. So these days, actually, smaller, right? The disk is getting really, really cheap. You can get several terabyte, for $50 these days. All right. So what kind of a technology does the flash memory has? It has two technology. One is the older one called the NOR technology. The other one is called the NAND technology. For the NOR technology, this is less like a disk, okay, more like a memory. It's byte addressable, so you can read a single byte from this device. Okay, for the NAND, these are page addressable, so when you try to read from the flash that's a NAND device, you can only read one page at a time. Okay, and one page is about 1 to 4 kilobytes per page, and then you organize these pages into blocks. Okay, they're 512 kilobytes per block. Okay, the advantage of NAND over NOR is that they are a lot cheaper, so they're suitable for these, very, very big, storage device, which is what we use for SSD and also for our flash card. Okay, if they're only byte addressable, they tends to be more, specialized, special purpose, memory devices. So we tend to use NAND, more. Okay, because they're suitable for file system use. The problem with the NAND is that there is a limit on the program erase cycle. Okay, so these kind of devices, you can only program it about 10,000 times. Okay, you can tell these devices to remember, data pattern, but you can only do it 10,000 times. After that, it says, you say remember or one, they say I forgot. Okay, so therefore these things have a limited lifetime. Okay, the write for these devices is that when you try to write to them, is that first you write a bunch of ones into them, okay, and then what you do is that you turn selected bits into 0. Okay, so the writing of ones, this is like an erase operation. It's like a memset, right? We say memset, pointer 0 or something like that. You clear out the a block of memory, and then you turn individual bytes on. Okay, so this is similar. These kind of devices, when you try to write to it, what you do is that you erase the entire page, okay, and then you say turn individual bits to 0. Okay, so you write all ones and turn them to 0. So it's the number of the cycle that's limited. These devices, when you do 10,000 times like that, then that device, or that memory location that you just do the erase and write, that location become unusable. Okay, so it's really hard to predict exactly which part of the device that will goes out first. So therefore, you do the worst case assumption that when you make so many writes, that your device starting to go bad. Okay, so if you have a device, let's say this is your flash memory device, this is block 0, this is the block n-1. Okay, if you tend to write to this location many times, you write this location 10,000 times. Okay, then at that point, you basically this entire device become useless. Okay, unless you do the same operation as the disk you can actually say that, oh, some of the blocks are bad, so I don't use them. You basically have to skip them. All right, so these devices, if you need to remember what blocks are bad, where do you remember these blocks are bad? Well, if you're going to have to remember them on the same device, and again, that will create another block that you're going to write often. So therefore, the device is going to go bad, fairly soon. Okay, so the trick to use these, flash memory, you can't really use it as is. What you need to do is that you need to make sure that the wearing on this the device is evened out. Okay, so when you try to write, you don't try to write to one location. Okay, you try to spread out the writes all over this device. Okay, so how do you do that? Well, you can use the log structure file system, right? If you have a log structure file system, then it's append only and never delete, right? So therefore, you can do that. Then every bit, at most you're going to write it only once. Okay, when you get to the end, maybe you have to, refresh it and then write it the second time. Okay, so so this particular idea of spreading out the writes is called wear leveling. Okay, you try to spread the writes across the entire device. Okay, and one of the common approach is to use the log structure file system together with something called the flash translation layer. Okay, so the idea over here is that this is your device. This is the flash device. Okay, you organize the flash as one long log. Okay, and if you go back to the the slides where we talk about the log structure file system, then you're gonna have your file system trying to keep track of where the data block is. Right, every time we write to something in the end, these are called INOMAP pieces. Right, and you have checkpoint file. Try to remember where all the INOMAP pieces is. Okay, so the checkpoint file needs to be somewhere else. Right, if the checkpoint file is on the same device, then the checkpoint file, those two memory locations is going to be written over and over and over again, and the device is going to go dead. Okay, so the idea over here is that you have another layer right here. It's called the flash translation layer, and this is often sitting on a separate device. Okay, so this is a layer that basically act like the checkpoint file in the log structure file system, where you have to read and write this layer many times. Okay, so this could be if you have a sort of a flash device, maybe you have another device sitting on that physical device that's storing the flash translation layer, or this could be part of your hard drive that actually store this information. Okay, so the idea over here is that if you can separate them, then you use this to keep track of what's written onto that disk. And once in a while, when you write all the way to the end, then you can basically reconstruct the entire file system by reading the useful data onto the hard drive and then start from the beginning again. So therefore, now you do the second time when you write it across the disk. So basically, you can erase the entire log and write data to it all over again. Okay. The next few slides over here basically tell you that you need to use the flash translation layer to remember where the data goes. So basically, it does the translation from a logical block to a physical block. Right, so it's almost like our checkpoint file, right? So if you try to write to location 20 is going to be a logical address and need to get translated. It's almost like virtual memory. Can translate into a device address. So 20 translate into 65, and now it remembers that 20 mapped to 65. Next time when you try to read from 20, it will point to this particular device, this particular block to read that data. Okay, and as you change them, it needs to remember what the data is being changed to. Okay, when you try to delete data from this, this file system, it gets a little tricky. Okay, so because the log structure file system was made so that it's append only and never delete. Okay, so therefore, in the end, when you use up the entire log, then basically you can reconstruct from the beginning all over again. All right, so so that's how we deal with Flash. Okay, and there has been a few file systems that are built on top of Flashes. I'm gonna skip all that. Okay, and then finally, this is the end of chapter 6. Briefly mention what kind of file system are on these popular system. Linux has 57 file systems built for it to date. Okay, so tons of people have been experimenting on the file system, even though these days we only use ext2, ext3, and 4. ext2 is a clone of the fast file system, right? And ext3 is exactly ext2 with journaling added to it for the sake of crash resiliency. Okay? And then ext4 is an extension to ext3. They added things like extends using the same technology as Windows NT. They also support a logical volume manager. Okay? And also they start using hash trees for directories. And I guess we didn't really talk about exactly what this is. And ext3, after ext3 done, there's somebody named Riser. They basically try to come up with the next version of ext3, and what he has done is that he anytime you need to look up something, he used a B tree index structure. Okay, so this is a very sort of interesting approach to try to have data structure on disk, everything to be B tree, and B tree are used in databases with very good success. So he believed that moving a file system into B tree everywhere also is going to perform really well. Okay, unfortunately, Riser was arrested for something. He's in jail, so the development of this thing stopped. I think he's still in jail at this point. All right, so we don't know what's going to happen with that. Oracle also, I guess Oracle bought Sun, Sun, and Sun has Solaris. They are also built on top of the fast file system, have something called the better file system done by Oracle. Windows NT, the NT file system uses extends, right? And we mentioned that extends has the problem of external fragmentation, right? So if you use the Windows file system, I guess one of the recommendations is that once in a while you have to run the program called defrag, right? The purpose of defrag is to get rid of external fragmentation, okay? For Linux system, Linux doesn't use extends, right? From your knowledge of this, the system right now, you know that any disk block is just the same as any other disk block. So therefore, you don't have to do any kind of a defrag operation in a Linux system. Okay, so extends has this problem. NTFS also use a B tree for directory lookup, and they use journaling for crash resiliency. Okay, Mac OS X has something called HFS plus in Mac OS X. I think the textbook mentions ZFS. I guess originally they planned to use that, but then they changed their mind. In HFS Plus, they use extends. They use something similar to B tree called the B star tree, and they use journaling. Okay, so you can see that all the modern popular operating system, they all use journaling, is because journaling is a really good way to provide crash resiliency, and it can be slapped on any existing file system. All right, the last slide in the file system, as I mentioned before, right? As I mentioned that if you only think that the file system has virtual file system and actual file system, well, that's really an oversimplification. Okay, there's a lot of layer inside the file system. So this picture sort of shows you, what kind of stuff actually goes into the file system these days. Okay, above here you have the user space. Over here you have the hardware. Okay, the operating system, you start with the file system. The next level, right? So the file system provide the abstraction to the application, the abstraction of files, directory, etc., the programming interfaces. Okay, the lower level is try to map everything down to the hardware. Okay, the next level is buffer cache, and we mentioned that it try to provide the abstraction that the device is very fast. Okay, so this buffer cache, that abstraction is purely there for performance purposes. Okay. Below the buffer cache, we have the logical volume manager This tries to present the abstraction that you only have a single device and not multiple physical devices. Below the logical volume manager, for the file system, there is this thing that that in the virtual file system you don't have to deal with this. It's the block device interface. We only deal with character device in Unix, right? But in reality, there is the block devices. This one presents the abstraction that a device is simply an array of blocks. Okay, so at this level of the block device interface, you address everything by block number. Okay, so you don't really know about sectors and cylinders and heads and things like that. That's down to the next level. Okay, and finally, the next lower level is a device driver. You try to map the block device into addresses on the disk, which means that they are sectors, cylinders, and heads that are maintained in the device driver. All right, so the real system is a lot more complicated. All right, so this is the end of chapter 6, right? All right, so now we cover 1, 2, 3. We're going to go back to chapter 4, right? And again, chapter 4, we talk about sort of an overview of the system. We talk about the simple system, but we skip the devices stuff. In the textbook, the device stuff is actually quite early in chapter 4, but we figured that we don't really need it in the kernel assignment, so we skipped it. Now we're going to go back to see what the device looked like. Actually, we talked quite a bit about devices already, right? We talked about device driver, what kind of function that has to be implemented, use polymorphism, to handle device read and writes, etc. How the device drivers are being implemented. Okay, so this section, the low-level kernel over here, we're not really talking about how devices are implemented, okay, because that's just device driver, right? And you have these array of function pointers, and then you use polymorphism, and they know how to use IO instructions to talk to the actual device over the system bus, right? So that's what it is. We're going to talk about some of the design issues in writing the kernel to support different device drivers. Okay, so that's what this section is about. All right. So the way we're going to do this, we're going to look at two special cases and to see what kind of things that the operating system has to come up with in order to support these two devices, even though these two devices look very similar, but actually they can be very different. Okay, and these two devices are terminals and network communication. Okay, so why are these things similar? Okay, so terminal is a physical device you can plug into the system, right? Network communication, well, this one is your network interface card, right? It's the one that has the Ethernet address, okay? And that's one's connected to the internet. And then when you try to get data from the internet, what operation do you use? You use read and write, right? Okay, all the devices look like files. So in order for you to talk to the internet, you use read, or you open and you read and write. Okay, what about terminals? When you try to read from terminals, well, you've been doing read and write from the terminal all the time, right? So reading and writing is also used to talk to the terminals. Okay, so from the user level, these devices are very, very similar. Okay, so we're going to talk about how do you support these kind of devices inside the kernel, because you have to use very, very different data structures and mechanisms to support these devices. Okay, even though the abstractions are very similar. All right, so this picture, this is the good old, it's called, I guess if you blow this place up, can I blow it up here? All right, you can actually see it. Over here, it says this is digital DIGITAL, so this is the Digital Equipment Corp. I guess later on they got bought out by Compaq, and Compaq got bought out by HP, and we don't know what's going to happen to HP. But so this is one of the company that made the the VAX machine and the PDP 11 machine. So they made terminals, and this one, I guess if I get rid of this thing, it actually says VT100. Okay, so this is one of the very, very famous terminal coming from Digital Equipment Corp. Okay, so in the good old days, this thing is plugged into the computer using a serial cable, and then so I guess I can draw that. Okay, so this is connect to the here's a device card. Okay, this is the terminal device. Okay, the terminal device get plugged into the bus, and here's memory, here's CPU, you know, etc. Right? Okay, so this is a serial cable connect to the back of the computer. Okay, so every time when you type a key, you generate an interrupt, and the interrupt service routine will invoke in the device driver. The device driver will read a character by doing one I/O operation to the terminal, the hardware over here, and this one will read a character from the device. Okay, every time you try to print something, you send something to the you use the device driver to send some data to this particular card, and then character will appear on the screen. Okay, so this device is both an input device and an output device. Okay, the screen is a character-based screen. It's 80 characters across and 24 characters, vertically. Okay, and it supports, in the good old days, these are called, character graphics. So you can actually, move your cursor to any place on the screen and say put a character there. Okay, so the device driver will actually have, ways to talk to the device to move your cursor anywhere on the screen and then put a letter there. All right, so this is a really popular system. Later on, there's VT200, VT300. And I think, so these days, when you talk about a terminal, right, when you install Ubuntu Linux, the program that you use is called terminal, right? Okay, so the word terminal actually means this terminal. Okay, it's the VT100 terminal back from the 80s or something like that. Okay, and inside your inside your login shell, if you're running tcsh shell or something like that, you can type in the command echo $term. Okay, and it will tell you what kind of terminal do they think that they're connected to. Okay, so this is kind of a fake terminal, but since the interface to the to the system, starting in the early 80s, are using this kind of terminal. From that point on, whenever we have a command line interface, we think we are sitting in front of one of those physical terminals. Okay, so when you say echo $term, it will actually tell you what kind of terminal you think you're connected to. And I guess these days you might see things like xterm. Okay, so that's an X11 terminal for doing graphics display. Or sometimes you can actually see something will say VT320 or something like that. Okay, so you know that these things map way back, to the 80s. All right, so whenever we talk about terminal, we should sort of think about we have a device that's looking like this, both as an input and also as an output. All right, so they're long obsolete, right? They're still relevant because now everything looks like a terminal in, Ubuntu. On Windows, when you run PuTTY or xWin32, what you see, a little window, that's also called a terminal. It's as if you'll plug into the machine that you're connected to. Okay? So when you say you run PuTTY on Windows or you run your xWin32, you secure shell to nunkey. It's as if you're sitting at nunkey, sitting right next to nunkey, sitting right in front of a terminal that looks just like the previous picture, and that one is physically connected to nunkey. Okay, so if you have root privilege and you say halt on nunkey, what you do is that you actually halt the nunkey machine. Okay, so this is very different from having a window interface when you have a web browser. When you have a web browser, you connect to the USC web page. You're actually still sitting on your machine, right? So the abstraction that's provided is not that you're physically at this machine called www.cs.usc.edu. You're making a remote connection, as opposed to this one is actually sitting at a terminal physically connected to that machine. All right. So when we think about this terminal, we need to pretend that we're actually sitting at that particular machine. Okay. All right, so to interact with this this particular terminal, you got to handle two things, right? One is every key that you type. Oh, no, by the way, where's the mouse? Yeah, there's no mouse, right? In the good old days, it's only purely typing on the keyboard and seeing things get printed on the terminal. Okay, so the character that you type will appear, will generate interrupt, will send to the operating system, and then when the user program tries to print something, you invoke the operating system to display stuff onto the screen. Okay, and by now you should see some code inside the kernel when you need to open devices, if you have a look at the code for the hello program, okay, you will see that what hello does is that it will open the device that are connected to the terminal, okay, and try to print data onto that terminal. Okay, so again, it's this terminal that we're looking at. All right. So the point over here in chapter 4, talking about terminal, is that when we thinking about implementing something that supports a terminal device driver, we need to sort of consider what are the things that are specific to this terminal that we need to support, and we need to support it very well. Okay, because in the end, if you have a device that you don't support very well, then people are going to say, hey, your operating system is really no good. Okay, because when I plug into the device, everything works in a funny way. Okay, so your operating system actually have to make sure that it works with every device well. Okay, all right. So you need to sort of think about what kind of characteristics are device specific. Okay, so in this case, you can think about all different kinds of terminal that is going to get plugged into your system. Some are manufactured by the Digital Equipment Corp. Some are manufactured by, it's like a terminal, like the one that is sitting right here. Basically a computer screen with a keyboard and stuff like that. You need to support all these different terminals from different vendors. And these days, of course, the terminal and the keyboard are two separate devices. One, get connected to the keyboard port, and the other one get connected to the VGA port or some other port. Okay, so they have different inputs, and we need to make sure that all these things are supported. Okay, so we need to support all these device-specific characteristics very well. But we also try to be as device independent as possible, because we don't want to end up writing one piece of code for one different piece of code for every device that we have to support. Okay, so some of the stuff we said we put it into the device driver. Those are vendor specific that talk to that particular device that are manufactured by the vendor. Okay, so the device driver need to know what I/O register to use to write to that device. But what about the kernel? The kernel, when they try to support that device, what is the minimum amount of things that it needs to support? Okay, as it turns out that when you try to support terminal, you can think about the terminal as a category of devices. They all require the same kind of support from the operating system. And when you talk about the network interface card, well, then you need different kinds of stuff. Okay, so if we think about the terminal as all the terminals put in together, what are the things that are device specific, and what are the things that are device independent? Okay. So if we look at all the terminals, there are some of the characteristics that are in common among all the terminal manufacturers. Okay, some of the problem that we have to solve in the kernel is that the terminal can be really, really slow, and the character generation is fast. Okay, when you try to print to the terminal, right, you do printf, okay, or you do write to the terminal device, and you can actually write a large memory buffer to the device. So those data can be transferred into the device at a very, very fast speed. And the terminal can be really slow, because in the good old days, you have to go through a serial line device connecting the terminal to the actual computer. Okay, so you have to wait for the device to get ready. Right, and again, we talk about how the I/O are abstracted away, and you can look at the ready flag, and then device driver can send data in one at a time. So in this sense, the application can actually overwhelm the terminal device. Okay, and you don't really want the application to keep rewriting to the device because the device is slow. So you sort of have to introduce some sort of a buffering between the application and the terminal device, so that you can sort of handle this speed mismatch between the application and the device. Similarly, when you try to read character from the device, you can type fairly fast. Okay, but can you type faster than the computer? Probably not, right? But the computer might be busy doing something else. Okay, so if you're typing into the program that's actually reading the keyboard, that program might be out to lunch doing something else, or maybe the operating system is serving some other processes. So all the keys that you type, they need to be buffered also inside the kernel. Okay, so 102 over here, basically you have the speed mismatch between the devices and the user processes. So you have to introduce some kind of a buffering, between them. Right, so the solution is that you're going to use two queues, right? One for connecting the keyboard, okay, connecting the keyboard to the application, and then one, printing data from the from the application to the device driver. So before you get the device driver, you got to have these data structure, and these data structure are kernel data structures. Okay, so these ones don't really belong to the devices. They are something that you have to use in the kernel because no matter what keyboard or what terminal you're connected to, you have to use the same kind of data structure to handle the speed mismatch between the device and the user application. All right, in this case, you need to use two queues, right? One for input and one for output. Okay, the way that this queue works is that if you want to write data into this queue, okay, what API do you use? Well, you use write, right? So this one you use write, okay, to write to this particular queue. So when you write, it's a system call. The system call goes into the operating system, okay? It's trapped into the operating system. All the operating system have to do is to take the data from the user and then enqueue it onto this buffer. Okay, then eventually the stuff in the device driver layer is going to pick up the data, okay, and then process it. When it's ready, it's going to unblock that thread, and then the user process can continue. Okay, so this particular data structure, while it could be used, we can use the bounded buffer, the producer-consumer code that we see to manage this particular buffer. Okay, so one of the things with the producer-consumer is that if the buffer is full, then one of the thread has to be blocked. Okay, so if down here the device is really not taking data as fast, eventually this buffer is going to get full, then the user will get blocked on the right. Okay, to handle data coming from the keyboard, again, the application has to call the read system call. If it doesn't call the read system call, then no data gets transferred into the application. When it calls read, then the data will go in. Okay, when you call read, and if the buffer is empty, then the user process is going to get blocked. Okay, and then you have to wait for the user to type something. All right, so interaction between the user and this buffer is basically using the read and write system call, and the system call needs to block at the right time. Okay, and these two data structure, you will use the bounded buffer or producer and consumer in order to handle the operation of these two buffers. Okay, what about the device driver side? Okay, should we use for every device driver create a kernel thread and using the kernel thread to interact with the device and writing data and to and from these queues? Okay, so as it turns out that doing a kernel thread, that's kind of like an extra overhead. You don't really want to have too many threads running in the kernel. You only want the one that you really need. So you don't really want to create one kernel thread per device driver. Okay, and so you end up with the stuff that we talked about already, that the way that you handle the other end of these two queues is to use the interrupt handler. Okay, when you get an interrupt, right, when you get a read-completion interrupt, okay, what you do is that in the interrupt handler, you do those two things. You start the next operation on the device, and also you unblock a thread. Okay, and similarly in the write completion interrupt, you do exactly the same thing. When you try to write to the device, as soon as that device is finished, you're going to generate an interrupt. You unblock the thread that's waiting for it, and also you schedule the next operation, writing the next character onto the screen. Okay, so this way you don't really have to have have threads running for every device driver. Okay, so these are the common things that you would do, inside the kernel. And I guess there's one extra case that's mentioned over here is that, if you queue some data, let's say you're writing to that particular device, and if there's no interrupt, then there's no interrupt handler to take your data. So the first time when you talk to that particular device, you got to make sure that you start off the device to start writing the first character into the device, and then from that point on, you set up the interrupt handler so that it will continue to pull data from the buffer. And eventually, when the last interrupt finishes and the buffer is empty, then at that point, it will remove the interrupt from the remove the interrupt handler from that particular device, and waiting for the next time you try to pull more data into that buffer. Okay, so there's some extra stuff that you have to do. All right, so that's that's the handling the speed mismatch between the device and the user program. There's another issue. So this again very specific to the terminal device, and it's something you need to handle for all the terminal devices. Okay, the input character may need to be processed in some way before they reach the application. Okay. in warm-up number 1 and 2, you notice that if you try to read, if you try to read a line from the input, if you keep typing and if you don't press the enter key, then your program is blocked. Okay, so it looks like you're reading one line at a time and not one character at a time. Okay, so that's what happened is that, so why do you need to do that? Okay, because what happened is that I want to type A, B, C, right, and I type A, B, and C. Okay, if these data go to your application right away, then there's no way for me to do a backspace. All right, so what happened is that, in order for you to sort of interact with this thing on the screen in a natural way, you want to be able to modify what you have entered before you press enter key. When you press enter key, that's your signal to tell the user process that, well, now you can have it. Okay, so therefore, before you can do that, you'll be able to back out this thing and then type a different character in there. Okay, so the question is, who is doing this? Is the kernel doing this or the user application doing this? Okay, think about kernel warm-up number 1 and 2. Do you want to handle all the backspace characters? No. So what you really want to do is that you want somebody else to handle it, and it turns out it is the kernel that's doing this. Okay, because this line editing of the current line, well, that turns out to be an operation that needs to be handled across all the terminal devices. So you might as well do that inside the kernel. Okay, so this one allowing editing, inside for that particular line before the enter is pressed needs to be done inside the kernel. All right, so how do we do this? Okay, so it's very important that once you take, if your application has performed read, once read returns into the application, there's no way for the operating system to ask for the characters to come back, right? The operating system gives these characters to the user, okay? And if you're doing a read, if you're reading a file, well, that means the cursor position has moved down, so therefore you really can't go back unless you perform a seek operation, okay? But if you're talking to the device, there's really no way to go back, okay? So you got to make sure that whenever you hand data to the user, then that data you hand to the user can never be modified. Okay, so therefore you have to wait for the character return to get pressed. All right, so in this case, we need to actually separate the data out, inside the kernel into two different kinds of data. One are the data that has already completed lines. Okay, so these are the lines that the user says, I will never edit this because I have pressed character return. Okay, and the other one is going to be it's called the partial line, and that is the one that the user is still modifying at the current time. Okay, so instead of having a single queue, now inside the kernel, for the queue that's going from the device to the user process, you need to have two queues. One is called the partial line queue, and the other one is called the completed lines. Okay, so inside the kernel, there's one more thing. In this case, when a character is typed, it should go to the display immediately. Okay, so in that case, this is called echoing, right? Whatever the character you type, you should see on the screen right away, right? Then when you take a backspace, you will see that character is getting erased. Okay, so again, all these things are done inside the kernel, but it doesn't really have to be done in the kernel. As it turns out, in Windows, those things are actually done by the application. Okay, so in Windows, if you want to write one of these terminal applications, the terminal handling application needs to do all these operations. Okay, in Linux and Unix, the kernel is actually doing the echoing. So whenever you type one character, it will actually send it. It will turn around, send it to the display device, and then display right there. Okay, and then when you try to backspace out of it, then it needs to tell the terminal to actually backspace one character inside the terminal. All right. So in order to handle this, if you do a little bit of analysis, and then you will realize that the management of these queues, they can actually be device independent. Okay. If you think about all the all the devices, all the terminals that you can plug into your machine, you can go to your market and buy anything you want. Okay. The handling of the backspace and the handling of the echo and stuff like that. Those things are actually device independent, right? I mean, if you handle backspace, well, it doesn't really matter if you're using a keyboard from digital or a terminal from Acer or something like that. The handling of the backspace or the carriage return, they're exactly the same. Okay, so therefore you have an opportunity to modularize the code inside your kernel and then divide things into device-dependent part of your kernel and device-independent. Okay, so this is almost like the file system, right? You have the virtual file system that's device-independent and the actual file system that's device-dependent or file system-dependent. Okay, so you do the same thing. So in this case, the part that's handling the editing of the current line, okay, or sending lines to the user application, that needs to sit in a separate module. Okay, and that module is device independent. Okay, so the name that's used for Unix and Linux system, this is called the line discipline module. Okay, and this one is device independent. Okay, so the device dependent part is the one that know what I/O register to use in order to talk about the device, while that still sits in the device driver. Okay, so now the picture becomes something like this. Okay, we're going to have two different module. This is the manufacturer specific driver. Okay, it's sitting it's in a separate module, and then the line discipline is the module that sits inside the kernel that knows how to manage the completed line queue. So every time you hit a carriage return, then it will send this line and then add it to the completed line queue. Okay, and they will start a new partial line queue, and then as you type characters in there, they will add characters to it, backspace, tab, or do all kinds of crazy stuff. So that's the job of the line discipline module. All right? So now the line discipline module will be managing the completed line queue and the partial line queue, and the data coming from the terminal driver, they get sent to the line discipline module, and then it will modify this buffer over here. Okay? Also, going data to the display, well, you only need one queue for that, and that's the output queue over here. Okay? So these things are separated into two different modules, and these things are all done inside the operating system. All right, so the line discipline module, what if you have, I don't know if you, because many of you have probably used international keyboard, right, not the US keyboard. So the way that we can handle, things like, Chinese characters and stuff like that is to have multiple keys to represent a character. Okay, so in that case, how do you handle multiple keys, right? This line discipline module only knows how to do English, for, backspace and stuff like that. If you want to handle, this is called character composition. Okay, if you type, I guess in the European keyboard, right, if you type backslash followed by the letter E, okay, if you type this thing, these characters will be echoed onto the keyboard, but as soon as you finish typing E, you will see that it backspace 2 character and then replace this by this character on the screen, the E with an accent, right? If you type the, single quote followed by E, and then you will see the backspace and then get changed into this character. All right, so this thing are done basically using a different line discipline module. Okay, so it depends on how you configure your keyboard to be a European keyboard or US keyboard or Chinese keyboard or whatever. You use a different line discipline module. All right, so that again is device independent. It depends on the user preference, so you can use different line discipline module. The terminal driver still is very device dependent. All right. All right. So when you design, the operating system, these modules, once you identify them, one question that you can ask is that where do I put these modules? Do they have to be in the kernel? Okay. The terminal driver, does it have to be in the kernel? Well, yes, right, because it's talking to the device I/O register. If you put in user space, you can't even use I/O instructions. So the the device driver has to be inside the kernel. Okay, but what about the line discipline module? Can it be, does it have to be in the kernel? Can it be in a separate user process? Okay, or can it be a library routine that are linked into the application processes? Right. So what happens when it's in the library, like a C library? Okay, if you put the line discipline module inside the C library, and then when you compile your program, well, when you do that, you're going to take the entire line discipline module and add it to your executable, and when you run those code, you'll be executing user level code. Right? Does that make sense for the line discipline module? Okay, so these days, I guess when you're designing your operating system, okay, every module that you create, you have to ask your question, where can it sit? And what's the best place for this module to sit? Okay, for the line discipline module, put it in a user library routine. Okay, so as it turns out, if you put in the user library routine, I mean, the idea over here is that you are sharing one device using this line discipline module, and then for every user application, they're all going to have a line discipline module in there. Okay, so that makes the device very difficult to share because in the end, you only have one physical device that will connect to your computer, and that's your that's your keyboard device. If you want to share among many user applications, then the right place to share is actually somewhere inside the kernel. Okay, if you put it all inside the user library where every user application get a line discipline module, then the code is going to be very, very messy. Okay, so it turns out that this, even though it's a possibility, but it's difficult to share such a device. Okay, you want the line discipline module to be only at a central place. Okay, so then you sort of get back to these two other choices. Where is the central place? Is it inside the kernel, or it can be actually in a separate user process? Okay, can it go into a separate user process? Okay, if you go into the user process, right, if you go back to the previous picture over here, okay, so putting in the user library, it's the same thing as saying that put it inside right here. Okay, so every application will get a copy of it, okay, and it gets a little, complicated. But if you put in a separate user process, like here's a user process, okay, I put the line discipline module in here, and if I only have one instance of this user process, well, then that can actually be done. Okay, the downside of this is performance, right? Because every time the line discipline module has to, go into action, this user try to perform a read, it trapped into the kernel has to come over here to this guy, and this guy has to come back into the kernel. Okay, so therefore, you're going to go to the kernel user, interface, 3 times instead of 1 time. Okay, so that's a performance consideration. Okay, so the main problem with putting the user process is going to be, it's going to be too slow, but if we have a way to make it fast enough, it will actually be a good idea. Okay, because then all your line discipline module will be, all your international line discipline module, the Chinese, the Indian, whatever, any nationality, you're going to have the line discipline module in user space, right? If I can put it inside this user process over here, the line discipline module, I can develop 100 of them. I can debug them without modifying the kernel. Okay, so there's really a big advantage of moving these things into user space, even though it might be a little slow. All right, putting in the kernel seems to be the best choice, and the downside of putting in the kernel is that, if you want to change anything in the line discipline module, if you want to add a new line discipline module inside the kernel, well, you got to upgrade the kernel. Okay, so that's a major problem. All right, so as it turns out that these days, if you think about a system like Windows or Ubuntu, we have the line discipline module running in user space. Okay, there's actually a separate process because modern days we deal with this window environment. Okay, in the window environment, you have many, many windows, and every window, you can actually direct them to receive keyboard events or mouse events. Okay, so in that case, there's something called the window manager that's managing all the keyboard and mouse events. Okay, so the window manager is actually a user process running in user space, and that could be the one that's actually holding the line discipline module. Okay, so the window manager will implement Windows on display, and then you can actually direct to say that all my keyboard typing will go into this application. Right? I mean, these days we know, right? Whenever we click on a window, the windows come to the top, and then whatever you type go into that application. Okay, so that application becomes the input focus. Okay, and that's the one that the window manager, whenever it receives data from the keyboard or from the device driver, it needs to forward that to that application. Okay, so the window manager is managing all these queues, one for every user process, and this is all done in user space. Okay, and these days when we use the windowing system, we know that the performance is quite acceptable. Okay, so that sort of proves that this particular scheme of putting the code inside user space actually works. All right, so the window manager is a controlling application. It controls this particular device, and it's handing out these events, these keyboards and mouse events to all the applications running on the system. All right. So I guess I'm gonna stop right here, and next time we're gonna, finish. I guess the goal is to finish chapter 4 in the next lecture. All right.
That concludes this lecture of Computer Science 402 with Professor Cheng. It's been Wednesday, July 23rd, 2014. From your sturdy operator Rex. Have a wonderful afternoon.
I signed the attendance sheet. I just want to make sure I signed it in front of my name.
Okay.